Yes, thank you. I want to thank the organizer for giving me this opportunity to talk here. And okay, when I got the invitation, I was really thinking what I should discuss in this conference. And then I decided to go for something that probably no one knows here, so that I will let's try to see something new about this quantum general dynamics. And I should thank for the collaboration where it is, my co-worker that made most of the job, Jérôme Dubail, Benjamin Douaillon, Paolo Ruggiero, and Stefan Scopa, plus others that will appear during the talk. So what is hydrodynamics? Okay, this is really nothing difficult. So hydrodynamics applies in, as EULER taught us, at an average scale between the macroscopic scale and the microscopic scale. What is the macroscopic scale? Is the scale on which like for the length scale is the scale on which the density varies, okay, which is just the density divided by its gradient. And the microscopic scale is the dimension of the atom, the separation of atoms or things like that. Okay, hydrodynamics is a description of the system which in order to be valid, there should be a window of scales between this microscopic and a microscopic scale. Else there is no hydrodynamics. Same thing for the time I'm not going to discuss here. Okay, so what the conventional hydrodynamics that we all know from undergraduate courses does, what it does is to tell that, okay, we can locally substitute expectation value over time with expectation value of some thermodynamics, okay, the Gibbs ensemble for ergodic system, obviously. And, okay, when we want to know how things vary in space and time, we should list the conservation law of the system that generally adjusts mass, momentum, and energy for a one-dimensional system. This conservation law produces some continuity equation between density and currents. Okay, and then solving this equation, one gets conventional hydrodynamics. That's what is done in undergrad. What is generalized hydrodynamic now? Is the hydrodynamic for an integrable system. That set of measured zero that Victor was mentioning, but still a very relevant set, as you will see in the following. So in an integrable system, there are not 1, 2, 3 conservation laws, but infinite of them, okay, which we can mention, we can call like QI. So these are the charges, and this is the corresponding density. And if we want to make the hydrodynamics of this theory, what we should do is to impose continuity equation for all these conserved charges. Okay, why it's not going now? Okay. Just, I will say that I will discuss very technical things without entering in any technical detail. So for the expert or for the people that are a bit knowledgeable in the field, just after the talk you can ask me whatever you want. But now I will just to give the introduction, just to give the way and the idea of what we are doing without solving any complicated hydrodynamical equation on the slides. So this, this conservation law are in one-to-one correspondence, according to theory of integrability, with the rapidities of the integrable model, which are what for a free theory is just the quasi-momentum, but for an integrable model, something a bit more complicated. But okay, if you don't know, if you know about integrability, you know what is rapidities. If you don't know what is integrability, just think to the free system as quasi-momentum. And as you know from free system, the set of rapidities that are populated in a system can be encoded in the occupation function, which is just the momentum distribution function of free fermion, for example. Okay? And so what we are going to do here is to want to substitute the expectation value over time with the expectation value of some statistical object, which will be a generalized Gibbs ensemble, okay, in which all these local conservation laws should be included. All in all, okay, describing this local generalized Gibbs ensemble amounts to have a rapidity occupation function, which depends on the position, on the rapidity, and on the time. Okay, that's what we need to know. Okay, for obviously, if there are more species of particles, there are more of this occupation function. But this is the goal of generalized dynamics, describing this quantity here. Just to tell, for free system, generalized dynamics was existing before generalized dynamics and has been developed by people like Bethlehem, Abanov, and Wigman, and many others that are listed here, and many that are not listed there, but it's not such an old subject, okay? Okay, obviously there were examples in the literature here and there, but as a general theory, I think it's something very recent. But, okay, how we can really describe this generalized dynamics? The discovery of generalized dynamics, as we know nowadays, came just a few years ago in 2016. It was two groups at the same time came out with the same idea. Okay, there were some interaction also between the two groups. Okay, and the one is by Olacia Castalfredo, Benjamin Toyon, and Takato Yoshimura. The other one, Bruno Bertini, Mario Collura, Jacopo Nardis, and Maurizio Fagotti, that probably many of you know the people. Okay, and what they build up in this two paper was this generalized dynamic that I will show just in a second, the equation. And okay, just to say that most of the work that appears here actually was done in SISSA, as both the group acknowledged in their acknowledgement, okay, because they were visiting us and they got this idea. But okay, this is just to say that, to show that something happened also in Trieste. Okay, so in a nutshell, what is GHD equation? Okay, so this is the generalized Gibbs the generalized hydrodynamic equation. It's an equation for the derivative, so it's a continuity equation for this density in rapidity space, okay, which is the usual continuity equation with the external force, okay, which is just the derivative of a potential, external potential if it's there or if not. And the really important guy is this effective velocity here. Here is not the velocity of the particle, but it's an effective velocity. What is the effective velocity? It's all the what the interaction do, okay? And again, here doesn't work, okay? The effective velocity that appears here is the rest group velocity, which satisfies this equation that comes from integrability, okay? The expert of integrability could recognize something very natural, okay? Which is just, you see, the effective velocity is the bare velocity plus something which depends on the density, and then a kernel which weighs the difference of the effective velocity between the value we are interested in and the other one we are integrating over. Okay? And this effective velocity actually happened in completely different contexts already in the literature before, and was, okay, probably the appearance of this velocity just before was one of the main boosts to get the generalized aerodynamic equation here, which seems very simple, and it is a simple equation, but to get there, okay, took really a lot of time. Maybe many people in the audience know about all the history of the calculation of the Drude weight in XXZ spin chain that people were working since, I don't know, 40 years likely, and no one was able to do. Okay, with generalized aerodynamics is few line calculation after it is solved thanks to this. But the point is understanding what enters here was the very difficult thing. Okay, but I don't want to make an historical talk right now. I want more to go to the future than to the past. Yes?
You said that the delta is the derivative of the phase of
Yes, the two bodies. No, it's the derivative with respect to the one of the two variables. Then you have a two body scattering variable, which is difference between the two rapidities, the derivative with respect to one.
With respect to velocity?
Yes, to the bare velocity, if you want, yes.
So maybe another question for basic understanding. So when you have an integrable system, hydrodynamics is good because it allows you to make predictions on late times for something you can't solve. For an integrable system, what's the practical advantage you get from doing this? It's again that you can reach times that otherwise I don't know with other integrable techniques you can't get. Because it should be still possible that you get no free meal here.
Look, free meals don't exist in, but what we are talking about, you have an integrable model, which is integrable when it's homogeneous, and now you make all the mess you want to this system. You put in a non-homogeneous context, you prepare in a non-homogeneous initial state, you let it evolve in a non-homogeneous Hamiltonian, you make whatever, all the things that appear in real life that one was just ignoring before, and this is, the hydrodynamics is exactly that. Okay, the system, a system in a non-homogeneous medium, an integrable system is not integrable anymore, okay? So what generalized hydrodynamics does is solve the hydrodynamics for this system. Obviously, at extremely long scale, the non-integrability will appear and will break generalized hydrodynamics, as it happened for conventional hydrodynamics, okay? At some point, the diffusion will take over, okay? And in fact, that's the difference between Euler hydrodynamics and Navier-Stokes hydrodynamics is just that you put diffusion. But this is an Euler scale hydrodynamics, which describe you the integrable system in a non-homogeneous background or whatever.
And it's still integrable or not? It's still integrable or not? What did you say?
We have a system which is, the Hamiltonian locally is integrable. It doesn't exist a system that is integrable, which is non-homogeneous. You need, you lose 0.0, which is conservation of momentum, okay? So if momentum, so a non-translational invariance many-body system is never integrable. Doesn't exist a single one. Okay, don't try to find it. It doesn't exist. Okay, so okay, you will see experiment later on, but okay. What is this time delay I'm talking about? Okay, this is easily understood in the case of, imagine we have just two velocity, which is one of the guys appearing in the S. So we have a velocity v, a particle velocity v, and a particle velocity w. What they do when they scatter, okay? You know that integrable system means that scattering is elastic, okay? This is also the non-expert heard this story. But what does it mean that scattering is elastic? That the particle exchange the two velocity, okay? But it's not like if they go continue straight. As you see from this very standard plots that is done in the case the particle have some finite radius, okay? You see that if you have an elastic scattering of balls, this is just kinematic of the third year of undergrad, okay? This is not very complicated. What happened, okay, when they scatter is that this particle here that now got the velocity w actually is not on the continuation of this line, but it's shifted. And the same happened to the other. This is the time delay delta, which is something that is generically compatible with integrability. So you have scattering, but still the particle don't, so you have elastic scattering, so they exchange the velocity, but they just don't go straight after that. This is a very basic concept, but imagine you apply many times. Okay, so you have one particle, one particle of velocity v that scatter many particles with velocity w. What happened? Every time you get a time delay. And if you integrate all this time delay, in the end it's like if inside this background of w particle, your particle that at bare velocity v actually will have velocity, a smaller velocity in this case, which results from all this scattering that are elastic. Okay, so this is a very basic concept that for some reason is it's hidden in the integrability equation, but it's very easy things to explain, okay? So this is what is happening. That's why the velocity that enters into the dynamic equation is not the bare velocity, because of the scattering with the other particle for a mechanism which in integrability is completely stupid, which is this one. Yes, sure. I didn't understand the question because the volume.
Could you define why you call these equations hydrodynamic?
This is a typical hydrodynamic equation. Now I'm explaining where the velocity that enters here enter. This is the density in momentum and n that appear here. Sorry, go back, please. Is the density in position and momentum space. This is the hydrodynamic for an integrable model, which is not a Boltzmann equation. Please go on. And the very important bit, as I was trying to explain, is that here there is this quantity which can be interpreted as an effective velocity, which depends, which is the solution of this integral equation, which never appear in Boltzmann, okay? So there is nothing like that in Boltzmann equation. And okay, which is the obviously it's an hydrodynamic equation that looked without this second line looks very much like Boltzmann. In fact, what Boltzmann does is another way of determining the velocity. But for the integrable models, which is the generalized hydrodynamic, the velocity, the effective velocity of the particle is what solves this equation, and what I explain in the next slide is where this equation comes from. So this is the logic of the story. Sorry if I was not clear at first. I hope also that this question allowed to clarify for the other. So now, okay, I'm a theoretical physicist, but still I want that my stuff appear somewhere. And in fact, GHD has been verified nowadays in several experiments, like this one in Paris by the group of Isabelle Bouchot, this one in at Penn State by David Weiss, and this one in Vienna that I'm not showing the graph, because, the plots, because they are not very, they don't contain much more information than the other. But so, what they did in this experiment, okay, they prepare our system in a double well potential, as you see from the initial distribution that is the one that appears here, and then let it evolve. It's a Bose gas with the Hamiltonian one-dimensional Bose gas that happens to be integrable, or almost integrable, so it's, again, the measured zero that turn out in nature. And you see in this system that if you let it evolve, this is, it's clear the experimental data are the noisy stuff, and the nice lines are the theory prediction, but they are really extremely compatible. And not only what appears here in this inside here is that this is the continuous line here is the evolution by generalized hydrodynamic that match extremely well the data. But this other dashed line that you can see, I hope, okay, is the prediction of conventional hydrodynamics that doesn't include the conservation law. Okay, so conventional hydrodynamics clearly is wrong. This system is integrable, cannot work conventional hydrodynamic, okay? And instead, the generalized hydrodynamic works very nicely. Okay, so this is the first experimental proof of generalized hydrodynamic, but another one that was also more interesting that appeared just last year is this one in the group of David Weiss, where they didn't measure the density, but they measured exactly the momentum occupation function in some as function of time and in some position. That's exactly what I was calculating before. And by the way, this is the occupation function of the rapidities, something that for the experts was considered a theory, some trick invented by the theorists to make calculation, okay, and was non-physical. But actually, as the group of data advice already did in a paper before, it's much easier to measure this quantity rather than, oh, I didn't start yet. It's much easier to measure this quantity rather than more standard observable. So let's be very careful when we say that some object is not physical. This is already the second time that a theory trick is measured, the other one being the entanglement entropy. So, yes, this is time of flight measurement, but then expanding the gas in 3D. If you make in 3D, you get the distribution function of the rapidity. Instead, if you make in 1D, you obtain the standard moment distribution function. So it's easier than, it's the easiest observable they can measure, and no one realized before. Well, it's, I found it very surprising, but okay.
But dynamics is iterable. State at equal to 0 is an homogeneous, but dynamics is iterable, and with homogeneous.
Yes, but we can make whatever, okay? Generalized dynamic can make, the only thing that you want is that the local Hamiltonian is integrable. Local. Yeah, I can make even a Hamiltonian that depends on time and space. No matter, I can do it. No, my generalized dynamic can do it. Then, by the way, there are free codes around now to use generalized dynamics, so it's just, you don't need even to solve the equation, you will find. So, as we have seen, generalized dynamics works extremely well. In this paper, here again, the theory is against the experiment and works all well. But so then why these aerodynamics should be quantized? And now please, if you were, this is my work that started 3 minutes from the end. So the point is that the thermodynamic limit that we are taking, you know very well, can be seen as the limit h bar that goes to 0 with n times h bar that goes to constant. It is constant, this is the usual semi-classical limit. Okay, but in this limit, many quantities vanish, and what we want to know, many important quantity, what we want to do is to compute exactly this quantity. Okay, so what we will do, I anticipate here, we will study linear sound waves on top of the classical generalized hydrodynamic solution. And then we will quantize them. This is the same thing that Landau did for superfluidity, and okay, skipping all the history, that probably what is more familiar to all of you is what Haldane did for Plattinger liquid. Okay, so what I'm doing here is basically bosonization of a non-homogeneous system. Okay, let's forget. Okay, so let's focus on a very clear problem. We make a one-dimensional Bose gas, prepare in a double well potential, exactly like the experiment in Paris, and then we quench to a single well potential. Okay, so the initial state is at temperature 0, it has entropy 0, and the entropy will be conserved by GHD equation. What happened for the generalized hydrodynamic? This is the initial occupation function in, for example, for a free system, what means this object? This is just the Wigner function, which means that these states inside here are occupied, the orange one, and outside everything is empty. Okay? When we make this quench, what happens is that the Wigner function starts rotating because that's what the harmonic oscillator does, rotates, okay, oscillates. And for the free case, it's completely trivial. What happens instead in the integrable case is that while it rotates, it also gets distorted because of interaction. But this is what GHD does. It's not new. Okay, this is what was, if you want, in the paper of 2016. What we want to do now, okay, so is to take this zero entropy GHD, which means that this is our generalized Wigner function, let's go like that. You see, if you cut at a given position, what we have in any point is a momentum distribution function, which is like split Fermi C. So there are chunks of Fermi C, okay, not a single one, depending on the position. Here you have just 2 Fermi points, as usual, but here you have 4 Fermi points. Okay, the theory of split Fermi C was known from this paper. Okay, and in these coordinates, the generalized hydrodynamic equation take the very suggestive form. So this contour is just parameterized by some xt of some parameter, s, which is the coordinate along this line, and theta, which is the quasi-momentum. okay? And the derivative of this vector will be just an effective velocity, that is the one of before, and an effective acceleration that also can be defined within generalized aerodynamics, okay? These are the same equation of before, but to the case in which we are in a zero entropy state, like this one. Zero entropy meaning that the equation function either is 0 or 1. Okay, I'm almost done, if it goes on. Okay, so what we want to do is to look at fluctuation around the zero entropy GHD background and quantize them. So what we do, what does it mean look at fluctuation? We don't have anymore a sharp contour, but we allow it to fluctuate. If we make our algebra, what we get is that at the classical level, there is a quadratic term here, a quadratic term that is connected to the derivative of the energy momentum with respect to the energy of the Fermi point with respect to the momentum. And since there are many Fermi points, this is a matrix of derivative. Okay? But so the calculation of this matrix again, A, comes from GHD. So it's not, by solving all those complicated equations, one can get the numbers here for this matrix. Then the quantum generalized aerodynamic equation is given with a bit of symplectic algebra that I don't report here by a quadratic form in which the quadratic term is exactly this matrix that I introduced before. Okay, so what is this equation? It's just a time-dependent, spatially inhomogeneous multi-component Latinger liquid. Okay, where the number of components depends on the number of Fermi points at a given time. Okay, so let's see what happened numerically. So this is the Lieb-Lineker model, again for a finite number of particles because it's difficult to simulate. And you see here, okay, so this is the profile as given by GHD, which is what was measured already in the experiment. And like if we consider the connected correlation function of the density, which will be 0 in GHD, okay, we see that they get some very funny shapes, especially at the when you have some transition from 2 to 4 Fermi points, okay, which are very well described by the data, and in particular, for example, also for the entanglement entropy, you see that entanglement entropy assumed this Batman-like shape. Okay, it was very nice to see Batman in a out of just both gas. Okay, this I skip also this, and just okay, take home message. What it is. First, the generalized aerodynamics provide an effective way to describe interacting quantum particles in one dimension. Okay, so this is, and this was already known. But the quantum generalized aerodynamics, that's what I discussed here, gives a way to construct quantum fluctuation around this generalized aerodynamics that also are accessible to experiment, and in fact, experiment to check these things are on their way. Okay, I will stop here. Thank you for your attention.